Hello everyone. In this video, we will focus on the brute force approach and similarly the exhaustive searching while designing an algorithm. Whenever we have a problem to solve, whenever you need to devise an algorithm, write a program to solve a problem, the first thing that we should take care is first make it run, then make it run faster. So that means whenever we have a problem and we would like to come up with a solution, so we first focus on the most basic, most obvious, simple, straightforward solution. And we call this the brute force approach. It doesn't have any smart decisions, any intelligence, any clever ideas in it. It is just a straightforward, very obvious, simple, direct way to solve a problem. Assume you would like to solve the problem of sorting. So let's make it this way, it would be better. Okay, so you have an integers and you go to a primary school, maybe a middle school student, and ask him or her to sort a given set of integers. What do you expect they will do? Most probably, they will first find the minimum element of the set, put it into the first position, and then find the second minimum and then the third minimum. So that's a straightforward way, right? So that is why actually we call this, and we will see it in the next slide, that is the selection sort. And this is the most obvious way of sorting integers. Similarly, we will be also focusing on how you can search a pattern on a text, or what is the direct way to compute a GCD. So these are all very straightforward solutions. When we talk about those straightforward solutions, in some cases, we will see some related problems here. So another way to approach the problem might be to check all possibilities, particularly if the problem that we focus on is a combinatorial problem, which means I have a set of selections and each selection will give me a result, and I would like to find the best one. Wouldn't it be easier to just check all of them? And this is called the exhaustive search. Okay, so in a space of possibilities, we are checking all of them one by one. Usually, such brute force or exhaustive search solutions, they serve as the initial solution, and further improvements, which come later. So they assume the brute force or exhaustive search as the baseline, and you can see that, okay, so by using such and such an approach, I improved the brute force approach or the exhaustive search approach by that much in speed or memory or something. So they also serve for benchmarking purposes, I would like to say. Okay, so let's visit those very simple solutions to some problems. As we said, the sorting. Okay, so I have here a set of integers, and then I would like to sort them. With the sorting, I mean from the minimum to the maximum. Okay, so an ascending order. So first, the basic idea is to find the minimum one, right? So you check all of those guys one by one, okay, and find that, okay, the minimum is 17. Once minimum is 17, what you do is you swap it with the first element. That is why you see 89 here on the second pass. What I did is, given the integers, I have detected the minimum one and moved it to the first position. Now I know that the minimum one is in the first position, so I don't need to worry about it. Now I will check all the remaining guys and find the minimum one. When I find that minimum, I just swap it with the first position of the new array. So that is why I will have this third step. as you have already discovered, I believe. Okay, so at each step, we are just decreasing the problem size by one. Okay, and now you have more and more sorted items here. And at the end, everything is sorted. This is called the selection sort because at each step, you are selecting the minimum element. If we check pseudocode for the selection sort, we out the complexity, right? The complexity. And the complexity is, in other words, is counting how many times if you make this comparison. The number of comparison is my cost. So in the first pass over those n integers, I will need to check all of them to find the minimum one, right? And then on the second step, I will be left with n minus 1, and then I will be left with n minus 2, so that goes on. So if you just sum these up, then we will see n times n plus 1 over 2, whatever, and this will be something, an element of O n squared. That means the number of comparisons that I will have with the selection sort is quadratic. So the time complexity of this algorithm is quadratic. Okay. Let me just clear those drawings. Once you have this basic solution, it's always good to think about improvements. I will tell you something now, but I will not provide the solution. So with the selection sort, at each step, you find the minimum. You find the minimum. How about this? At each step, at each iteration over the array, I will not find minimum, but instead I would like to find both minimum and maximum. Okay? So if I pass over this initial sequence, in my new algorithm, what I will do is I will find the minimum, also the maximum. So in the next step, I know that the minimum is here and maximum is here, and whatever remaining, it is in between. So you are decreasing the size of the problem, not by one, but by two here. And by finding minimum and maximum in one pass. However, the number of comparisons you make while finding minimum and maximum should be something advantageous for you. So the question here is, whenever I have an array of size n, can I find both minimum and maximum by making less than 2n comparisons? Okay, so I don't want to make 2n comparisons. I would like to make something, okay, less than 2n comparisons. Just think about it, and then you may come up with a new selection sort. And what I can suggest is, once you have this new input selection sort, just write the pseudocode and see whether you are gaining an advantage in time complexity. Is it better than O n square, or is it still O n square, but with a smaller hidden constant? Okay, just think about those questions. Anyways, okay. We said that the brute force approach is straightforward and obvious and doesn't have any clever findings, but I think this might not be the case all the time because I like bubble sort, and bubble sort, I believe it includes some interesting ideas. Okay, so with the bubble sort, what we do is whenever we are given a sequence, okay, so this is my input sequence. In one iteration, what I do is I just compare the consecutive elements. And always make the left one less than the right one. So whenever you compare 89 with 45, since 45 is less than 89, what I do is I swap their positions. Now 45 is here and 89, it is here. I continue. I just compare 89 with 68. 68 is smaller, right? That is why you just move this guy to the left, and this one continues its journey. Okay. You compare 89 with 90. 90 is greater, so there is no need to make a swap. Now you compare 90 with 29, so it requires a swap. So 90 comes here, 90, 34. Okay, 90 is still continuing its journey, and 90, 17, yes, 90 arrives to the rightmost position. The moral of the story with the bubble sort is, while your journey over all the numbers here, sooner or later, you will hit the maximum guy. And once you hit the maximum guy, this maximum guy will always replace with the consecutive with the neighbor. So it will keep bubbling up until the rightmost position. In other words, with the bubble sort, the maximum element moves to the rightmost position at the end of this iteration. Okay, so let's see how many comparisons I made during this first iteration. I compared these guys, I compared these guys, I compared these guys. If I have n elements, actually I'm making n minus 1 comparisons, but we are making a theoretical analysis, and n minus 1, n plus 1 doesn't make much sense, so you can assume that, okay, so I am having n comparisons, and at the end of n comparisons, I am fine with the position of the largest element. What you will do is you will repeat the same thing with the remaining list. Again, you will be comparing the elements, and you will make here at this time n minus 1 comparisons. At the end of those n minus 1 comparisons, you will have the largest one moved to the rightmost position. So in this way, n comparisons, n minus 1, n minus 2, again, you will come up with the quadratic complexity. So this is the bubble sort. And here is the code for the bubble sort. Okay, so as you see, this is again 2 for loops. And if when you compare aj plus 1 with aj, you always make sure that the smaller item should appear on the left. Okay, so this is the bubble sort. What else we have? We have the string matching. Again, the brute force straightforward string matching requires you align the pattern to the text position 1. Okay, so leftmost text position. And you start comparing the symbols one by one. You compare the first symbol of the pattern with this first symbol of the text. Second, third, okay? Until you get a mismatch, or you have all the symbols of the pattern matched with the text window, okay? That means in the worst case, what will happen is, okay, I will just compare this one, this one, this one, this one, this one, and this one. At each alignment, I will compare all the elements of the pattern with all the elements in the current text window. And in the next step, I will shift the pattern to the right by 1 position. Again, I will be doing the comparison, but this time I'm comparing the first symbol of the pattern, now the second symbol of the text, because the window starts in the second position, and third, and that goes on. Okay. So at each alignment, assuming that the pattern length is M, I'm making M comparisons, right? And what will happen in the worst case? I will be making this comparison, M comparisons, and I will need to repeat it how many times? N minus M, I guess, plus 1 times. Okay, because in the last alignment, so you will be aligning your pattern of length M with the last M symbols of the text. Okay, again, this part is not important, and actually, in the worst case, the number of comparisons you will need in the brute force string matching is equal to N times M. N is the text size, and M is the pattern size. Since we know that M is something less than N, you can also say that M is something ON. So ON times ON, so that's actually equal to a quadratic timing. Okay. Maybe it might be interesting to think about the worst pattern, okay? Worst case pattern and worst case text. How about this one? So there might be some others, but A is my text, and my pattern is B. Okay, so that means at each iteration, at each alignment, the first element will match, the second element will match, but the third one will not. And then you will move it to here. So the first element will match, the second element will match, but the third one, it will not. Okay, so this way you will need to make 3 comparisons at each alignment. And how many alignments I will have? 1, 2, 3, 4, 5 alignments. That is because the text length is equal to 7, right? And your pattern length is equal to 3. So 7 minus 3 plus 1 is equal to 5. So you have 5 possible starting positions. And the total number of comparisons will be 3 times 5. It is equal to 50, right? So surely this can be tuned such that it is AA and ends with A. So that means I will be sliding the pattern over the text. And at each alignment, I will compare all of those guys and will report a match. There are tons of different string matching algorithms that perform this, not in quadratic time, but linear and then less than linear, sublinear times expectedly. And we will see some of them in our future lectures. Okay. And what else we have? Here, I wanted to include some harder problems. You know, the traveling salesman. So we are given a graph. On this graph, the vertices are connected with edges, and on each edge, we have a weight. Our aim is to start from a vertex, visit all the others, and come back to the starting position. But during this travel, we would like to have the minimum cost as the sum of the weights on the edges. For instance, let's assume I start from A, okay? I start from A, I go to B, B to C, C to D, D to E, and E to A, okay? So the total cost is, right, 7 plus 3 plus 6 plus 7 plus 1, right? I guess it is something 24, right? Okay, so A, B, C, D, E, A. So that happens with a cost of 24. There are some other possibilities, right? What I can do is I can go from, let's say, let's read it this way, A to D. Okay, so A to D is equal to 1, D to C, C to B, B to E, E to A. I can do it, right? So A to D is 1, D to C is 6, right? C to B is 3, B to E is 8, and E to A is 1. So if we just sum these up, it will give us something, I guess it will be something 19, okay? You see, then what I can do is I can try all possible permutations of those vertices, A, B, C, D, E. I know some of those permutations will not allow me to make the complete cycle because there might not be an edge. For instance, if you say that I will go from A to C, there is no edge from A to C. So this will not be valid, okay? But I will skip it. But moral of the story is, if I try all possibilities, then I will find the minimum cost, right? So that is for sure. But you know, what is the number of possibilities if you have n vertices? N factorial is the number of possibilities. And you know, n factorial is a horrible function when n becomes even with the small values, even with when n is equal to 20. So n factorial is something like 2 to the 64. Actually, it is larger than 2 to the 64, okay? So that is why this is an exhaustive search of the space. However, only works when n, the problem size, is small enough. Another such problem is the assignment problem. So with the assignment problem, what we have is we have some number of persons and we have some number of jobs. Okay. Each person will be assigned to a job. And at the end, what will happen? We want to have the minimum cost. The cost that person one achieves job one is 9. Job 2 is 2. Job 3 is 7. Job 4 is 8. And these are the costs for the person 2. These are the costs for person 3. And these are the costs for person 4. Again, what would be the straightforward solution? So I can make a random assignment and I can pass over, I can just list all possible assignments. Person one can be assigned to job 1, job 2, job 3, job 4, right? So there are 4 possible assignments for person 1. Whenever you pick a job for person 1, so let's say I choose job 3, what will happen is person 2, it has only 3 possibilities left. Person 3, it has only 2 possibilities left. And person 4, the remaining job will be assigned to person 4. Again, similar to the previous one, the number of possible assignments is again n factorial because I have n person and n jobs. And I can exhaustively search all possibilities and return you the result. There is a better algorithm for this assignment. So we call this the Hungarian method. Actually, that is something like the Gaussian elimination, but we will see that later. Do I have anything left? So yet another difficult problem is the graph coloring. We are given a graph here, and on this graph, my aim is to give a color to each node, to each vertex, such that its neighbors will not have the same color. For instance, if I assign blue to this node, to this vertex, so who are their neighbors? It is this one, and this one. And you see, none of them is blue. That makes it a valid coloring. So these two guys have red, and this one has a yellow. And you would like to preserve this rule for all the all the nodes. And the point is, I would like to use minimum number of colors, because if you give me n vertices, I can use n colors and it is done. However, I'm trying to find the minimum number of colors. Okay. Again, the same story. I can start from a vertex and then do a traversal, okay, visiting all the others. And during that time, I will check at each step whether I can use a color or not. So here is an algorithm to solve it. Okay, so this is actually a greedy algorithm. We will be maybe studying this further when we study the greedy algorithms. But the thing is, I have a list of colors, okay? So, and these are color 1 to n. And I have the list of vertices. For each vertex, what I do is I check whether I can use color 1. If not, then color 2. If not, then color 3, up until color n. And this check color part actually does the job. Whenever you say that, okay, I would like to color this vertex V with this color C, is it valid? What happens is this g.checkColor just goes to the graph, finds the neighbors, incident nodes, check their colors. If there is no violation, it says that, okay, so you can just assign this color. Okay. Once you assign this color, you don't need to check the remaining colors and you go with the next vertex. However, with this algorithm, the visiting order makes great sense. If you visit this example in the order 1, 2, 3, 4, 5, 6, 7, 8, okay, so I assign the first node red. And for the second, can I make it red? Yes, I can make it because there's no connection between 1 and 2. When you go to the third one, can I make it red? No. That is why I need to choose a second color. Okay, now I choose yellow. Now in my color palette, I have red and yellow. You go to 4. Is red allowed? Yes. You go to 5. Can I use red? No, you cannot, because there is the neighbor 2. Can I use color yellow? Yes, you can. You go to node 6. Can I use color red? No, it is a neighbor of 4, and 4 is already having the color red. Can I make it yellow? No, it is a neighbor of node 5 who has the color yellow. So I have nothing left, so I need to add a new color, and I will make the 6th node green, right? And I continue with the 7 and then with the 8. And at the end, we see that I need to use how many? 1, 2, 3, 4 colors. But if you try it with a reverse order, okay, you will see that it might be possible to make this graph coloring with less colors. So again, the same idea. So once you have n factorial, all possibilities, a straightforward exhaustive search over all possibilities, sooner or later, you will hit the minimum one. Okay. So that is all I guess I can say about the brute force and exhaustive search approach, but it may take your attention that for some problems, for the exhaustive search problems, we always have n factorial possibilities. No, it is not the case. That is why I believe I need to give you another example. So let's focus more on another one. So the subset sum problem. With the subset sum, they provide a set of integers, and the query is there a subset of this given set such that its elements sum up to a queried value? Okay, so I will give you an example. Okay, I hope you can see this board. So let's say I have this set, okay? 2, 1, 5, 7, so let's say 3. Okay, this is the set. And the query is there a subset of A such that the elements sum up to 11? Okay, actually, I see that if I sum 3, 7, and 1, this will be equal to 11. So that means the subset 1, 7, 3 is an answer for this question. However, uh, to make an exhaustive search, what I will do is I will say that, okay, I need to generate all possible subsets of this 5 element, right? How I can do this? I will just use 1 bit per each element, okay? 0, 0, 0, 0, 0. Okay, so assume this bit is devoted to this element, this bit is devoted to this element, this bit is devoted to this element, and this way, okay? I have a 5-bit counter, and a 5-bit counter can take how many different possibilities? It can take, right? 2 to the 5 is equal to 32 possibilities. I will write all of them. And whenever I would like to check a possibility, okay, so let's say it is this one, that means, okay, 1 is in the set and 7 is in the set. Why? Because the corresponding bits are set to 1. The others, they are not. And 1 plus 7 is equal to 8. It's not equal to 11. So this is not a correct assignment. If you make it 0, 1, 0, 1, 1, then this will be a 7, this will be a 3, and this will be 1. This will make 11 true. In other words, if you have n elements in your input set, okay, by passing through all 2 to the n possibilities, you can check whether any one of them hits to the queried sum. So this is the subset sum problem. Surely there are better solutions for all those hard problems. I mean, maybe not the exact solutions, maybe some approximations and some better heuristics. So we will be studying them further in the upcoming lectures. But that is all I can tell you about the brute force and exhaustive search approach. Okay, so these are the most basic line of algorithm design. And on the next lecture, we will start by decrease and conquer, divide and conquer, and transform and conquer type algorithms. Okay, take care and see you soon.